So what I would like to start out with is just two simple examples of work that we've done since we've acquired the PI-89. The first is what I would just call it the classical brittle to ductile temperature transition. So when we first got this tool and just in discussions with Hysitron, Bruker Hysitron, we were discussing the idea of what could we use to be a really nice case study to really look at mechanical properties as a function of cryogenic temperatures. And so we immediately thought of DBTT type behavior. And so for those that aren't familiar with it, for example, in BCC metals, they undergo this transformation that at high temperatures, they experience sufficient ductility or plastic deformation, but at lower temperatures, that same material can exhibit brittle behavior. And so there's a temperature transition where you see these differences. And so what we began with is we said, well, what we do is to look at two different type of ferritic alloys with different carbon content, because carbon content is known to control that DBTT temperature. But also when you add carbon into steel, for example, you actually precipitate out a cementite phase, a ceramic phase called Fe3C that produces a lath-like structure called pearlite. And that's shown here in the bottom left image, a micrograph of that lath-like structure. And so what we have is the volume fraction of this pearlite phase, which is alpha iron or ferrite iron and cementite, is going to be controlled, that volume fraction will be controlled by the amount of carbon concentration. And of course, the spacing that we see is going to be a function of the composition as well as the undercooling the alloy undertook. So with that in mind, we just took kind of off the shelf two general materials. One was a 1095 steel, and then which is shown here to the center, and then to the far right, we looked at a pearlite gray cast steel. And in both of these conditions, we're going to form this pearlite microstructure within the grains, but we're also going to have some other phases. As you can see in the 1095, these large dark contrast grains are just simply cementite, and then in the cast iron, because we have a higher concentration of carbon, we produce this fibrous looking carbon phase as well. But within both of these materials, in the microstructurally at the grains, we're actually going to have that pearlite microstructure. And so what we wanted to do is to take advantage of micromechanical testing that you can do with these type of tools by being able to sample within one or a few of these grains where that pearlite structure existed. So we could avoid, for example, the large cementite grains, or in this case, the fibrous carbon second phase that occurs in the cast iron. So with that in mind, we just used a plasma fib and a gallium fib. So in the upper left corner is just some of the general parameters we use. So we use 30 kV, 15 nanoamps of the Xeon plasma fib to run rough cut out a micro cantilever beam that's generically shown below in that schematic. And then we did some final polishing of that beam at 1 nanoamp. And then we used our gallium fib to cut the actual notch that we would need. And then, of course, to the right in the middle that you see here, this is simply an image of the schematic of the pearlite structure, which is denoted by the different laths. And then we call lambdas, just basically the spacing between those laths. And like many experiments, this was very preliminary. When we got started, we just really wanted to take advantage of having the capability of the cryogenic testing and what we can learn from it. And so obviously many experiments that after you finish it, you look back like these are differences that I would do before. So I really would like to cusp this discussion in terms of like a preliminary looking at how the PI-89 can be used in studying micromechanical behavior, at least for the DBT examples. So we performed 3 different cuts. One cut has the beam being perpendicular to the lath interfaces, as generically showed here in this cut 1 schematic. We made another type of beam in which the laths are now parallel. The major axis of the beam is parallel to those lath interfaces. And then we have a cut 3 in which the beam is now cut at some angle, roughly about 45 degrees to those lath-like structures. So we have temperature variations, we also have lath orientations, and the like. And then if we look generally at the microstructures of our 2 samples, our 1095 steel and our gray cast iron, we see that the spacings are roughly the same, slightly larger for the ferrite structure being the 1095 because it has a lower carbon content, and that also the total number of laths that we could capture within our beam based on that spacing, and that those are just roughly approximated in this table below. So using that, this is just kind of a video that shows the behavior. Let's see if this actuates, and I'll let a couple comments I'll bring out, just experimental realities. One thing that you can notice is clear icing that occurs. So of course, I'm in Alabama, the humidity. When you cool things, you're going to get some water condensation in that's going to form ice. Now, this can actually get removed if you allow the system to pump for a sufficient amount of time. Those effects can be, the icing can will then eventually be removed from your sample. But in our case, we wanted to look at the mechanical behaviors, and we just noticed that the icing was clearly just on the surface as well as on the indenter itself. And so let me start this. And this has been sped up as well, just to speed up time. But what you can see is we're pulling it. We see some notch widening, some cracking, etc. This is kind of a nice live video. And this is, again, one of the advantages of doing things in situ is you can correlate the quantitative load and displacement values to actual images that occur in the deformation of the material itself. And so in these snapshots, you're just kind of just generally showing you what are some of the features that we observe. Well, obviously T1 is really at the initiation of our experiment where we've made our fib-based notch. As we loaded it, we can see and measure actually how the notch is widening. That's how most of the deformation is being accommodated at this point. And then we are able to see initiation of a crack, a clear indication of a crack that formed at our notch. And then as we continue to provide more and more load to the sample, we can see diverging of that crack. So not just going vertically down, but we see some contrast that appears to show that the crack is also diverging to the right of viewing to the right of our initial crack that forms. So with that information, what we now do is now one of the things you can definitely see is when you take an SEM image versus a video capture, you get very, very nice images. But what we have here is a set of our 1095 steel in which the laths are perpendicular to our beam direction and our notch here. And this is before the test, after the test when it ended, and we did 2 samples of each, and here's the other end of the other test as well. And in both cases, what we really saw was we didn't see a brittle response. We see this loading and then neoplastic response here. Now you'll leveling here on test 2. Now in test 1, we see it rising, but then we see a drop. Now, again, people that have been doing this work for years probably recognize what this is, but for those that are just getting started, what happened in this case is that while we're using an indenter to fix and hold against the beam, it actually slid, and that sliding is a response to the material exhibiting some ductility, which was surprising to us, and then it leveled out again. Now, if we go to the cryogenic temperature, in this case, we were actually able to get down to minus 160 C, even though it's spec'd out at 150 C. In this case, we were able to go about 10 degrees lower. And here our laths in this example are at an angle about 45 degrees to our notch. And then in these cases, we again see this load and then relative flat behavior. We do not see a drop in the load that would be consistent with a brittle behavior, which was very, very surprising to us because we figured by this temperature and these conditions that we would definitely see a drop in the load and a clear a catastrophic crack that occurred. Even though we did see some cracking, it did not manifest itself into a dramatic quantitative drop in the load. Now, if we compare this to our gray cast iron, here you can clearly see we have a lot more laths that have formed because of the smaller spacing, because of the higher carbon content in our sample based on the volume fraction. And one of the advantages, again, I just say with doing micromechanical testing, we're able to go to a single grain that's quite large, mill out our sample, as you can see here, and then test it in without any additional grain boundaries, just looking at the lath interfaces. Here, again, the laths are perpendicular to our major axis of our beam. We've loaded it. We see our notch, and what we again observe is primarily notch widening in the sample. And here's its load and displacement response. Again, we're not seeing a brittle response. Now, in the case of when we made the notches now parallel to the major axis of the beam, as you can see here, you can really see the laths are parallel to our major axis. We actually see what we'll call a quasi-brittle response. It didn't just catastrophically fail, but we do see that as we loaded the sample, a decrease in the load as we continue to apply more and more load to the sample based on this displacement. And so while we don't see the classic brittle response that we had anticipated, we do begin to see, at least in this orientation and at this temperature condition, that we are able to see a quasi-brittle response in the sample. And so again, this was a real initial test of just saying, what could we do with the P99? What are some of the opportunity spaces that we could pursue? And what's involved in making, for example, microcantilever beams. So our preliminary observations and forward opportunities, I think what we can see here is, one is that, interestingly, we saw no clear brittle response.